think it's a really relevant topic for those of you who are interested in doing numerical simulations of astrophysical plasmas, or just numerical simulations in astrophysics and physics in general. My work is in simulations of galaxy clusters, but I've also spent a lot of time being a developer for this package I'm going to talk about, YT, which is really helpful in terms of doing analysis and visualization of these kinds of simulation data. So I think if you go to the Slack channel, you'll find a link to this talk, which you can follow along if you want. There's some arrows at the bottom and the lower right. We're hoping to organize like a focus session to actually work through some examples with some of the data I'm going to show today. But you can actually download that data here at this URL. So if you can get this URL, which should, like I said, should be in the Slack channel, and you can follow along and you can get these links to the data and some of the examples. So first of all, what is this thing we mysteriously call YT, which, by the way, stands for yours truly, and if you're asking me why that is, I don't know. You'll have to ask Matt Turk, the original developer. So I apologize, there's the first typo already. So YT is a framework working with the outputs of simulation codes. And it works with it and provides, interfaces, physically intuitive interfaces to do things like visualization. So some of the things we've already talked about in the last two sessions from Tamara, which were great. Slices and projections, volume renderings, phase diagrams, everything that you're going to need at some point to put into a paper. And analysis, looking at like data selection of your simulations, derived quantities, low-level data inspection, profiling, in other words, how does a quantity vary with radius, density, and a lot more. So in terms of being able to understand and ingest data and read it and help you analyze it, YT supports already many production astrophysical simulation codes. I doubt there are that many SPH people here, but in case you're here, you'll be happy to hear that we've got support for Gadget and a couple other codes. Patch-based AMR codes such as ENSO, Athena, and Chombo data, Octree AMR codes like Flash and ART, as well as some unstructured mesh data as well. And YT runs on a variety of platforms. Runs on Linux, Mac OS, Windows, including the new Bash on Windows if you're running that on the Windows 10 beta. Runs on everything from laptops, the one I'm giving the talk from, to supercomputers on NASA's Pleiades. I was doing that just earlier this afternoon. Currently runs on both Python 2.7 and 3.5, and source installs and binaries are available for most of these platforms. What's really great about YT is that it's developed by a global team of astrophysics researchers to solve their real-world problems. It's great that a lot of the development has been done by people who are not only knowledgeable about Python and about visualization, or at least trying to make themselves more knowledgeable about the computer sciencey stuff of it. They're developing it with a mind towards astrophysical applications. So this is just like this is a sample of all the people who have made like some great contributions. So-King Ji is in the audience today, so I want to give a shout out to him. He's on this list. And as I mentioned, we have levels of support for various codes. So I'll just kind of scroll up and down here. By the way, this talk, in case you're not familiar, is being given out of a IPython notebook, which has been converted to slides. So if you want to ask me about that later, I'll definitely be happy to do that. But here's part of our webpage where we're showing some of the codes, the various codes in astrophysics that we support, and also data formats that we support, and the various levels of support. And if you go to our website, if you're not quite sure how to use it on your data yet, but you want to try out some of the examples on our docs page, which I'll give you a link to later, we provide example data sets for a number of these codes. So you see here we actually have some Athena data sets that you can download here. There's also some Chombo data sets, ENSO, Flash data sets, Gadget. There's even a Chandra events file down here. If you're curious about that, you can also ask me about it later. So while I'm talking this up, I may as well just sort of get started and get with the basics of what YT actually is and what it can do for you. And these slides have been heavily adapted and added to from some 2 talks by some other great YT developers, Britton Smith and Nathan Goldbaum. Before I do that, since I'm not sure that everybody in here is quite familiar yet, I want to talk about, it's probably a bit circumspect for me to distill all like astrophysical simulation data to these 2 categories, but for our simplistic purposes today, I'll do that. When we're talking about volumetric simulation data in astrophysics, we're generally talking about 1 or 2 things. We're either talking about Eulerian data that's laid out on some kind of grid like this that may have an adaptive mesh, whether changing adaptive mesh refinement or a static mesh refinement. Here's an example of that. This is a slice of the magnetic field strength in a simulation. You can see that the different resolution blocks indicate that the resolution is changing. But then you also have, and again, as I've mentioned already, you have codes like Athena, Flash, Enzo that are of this category. But you also have Lagrangian particle-based smooth particle hydrodynamics data that handles the equations of hydrodynamics in a more Lagrangian way. Gadget is a prominent example, gasoline, Tipsy. And so I'm going to be focusing more on this kind of data on the left today, in fact, almost exclusively, because I suspect that that's what this audience is mostly about. But just let it be known that we also have support for this type of data as well. Okay, so let's look at another sort of a schematic of this exact thing. So this is what an adaptive mesh refinement data set might look like from the perspective of the way it's laid out in the data file. So let's see some aspects here. This doesn't look particularly physical. So you have these grids of different sizes. It may be the coordinate system is often in something we call code units. So it doesn't necessarily correspond to like centimeters or kilometers or anything like that. It corresponds to something that numbers that are around 1, to sort of help, to make it, computation a little more saner. But the point is that when you're just thinking about the data, you think about it like this. This is not ultimately what you're after, right? What you're after is the physics that you want to get out of the simulation, the predictions you want to make. So YT lets you take that rather abstract data representation and lets you think about the data using a physically motivated interface. So one thing it gives you is unit awareness. So it takes that 0 to 1 or -1 to 1 or -2 to 2 or whatever it is, and it converts it to the units that it actually is in based on the unit specification that it either reads from the file or that you tell it what it is. So in this case, we're saying this is a box of like 10 megaparsecs on the side. And in terms of thinking about data using a physically motivated interface, where I'm going to discuss the entire talk basically going to be discussed in terms of these fundamental concepts, which I'll explain in turn: data objects, fields, units, and derived quantities. So the best way to explore how we can think about the data using a physically motivated interface is to actually load a data set up. At this point, I should say that this talk contains a lot of code. I'm hoping that we can have like a focus session where we can actually do some code. But for now, it's probably best to just sort of get the broad's eye view of what we can do and not worry about the particulars of the code. But if you have questions, you can definitely ask them. So what we're going to do here is that we're going to load one of those data sets that I mentioned was available for download. This is an Enzo cosmology data set using this simple Python line here, yt.load something, something, something. Gives you a data set. It'll immediately print out some basic properties of the data set, the current time of the data set, the domain left edge and right edge. Because this is an Enzo data set, they seem to be obsessed all the time with going from 0 to 1. So that's what it is. And the point is that we want to think about this data set from a physical perspective. So often in astrophysics, we're asking questions like this. I have say a cluster of stars or a cluster of galaxies or something at this position here. And I'm interested in what's going on inside a sphere of some radius, in this case 2 megaparsecs. That's your physical question, not your computational question, but your physical question. So what YT does is that it takes the physical question and the computational answer and bridges them together by focusing on only the data that you want to select that's relevant to your question. So you can see here, We've got a sphere, and YT is handling the data selection of the cells on the grid that correspond to that sphere. And that brings us to the concept of the data objects, which are these geometric shapes that are physically relevant that you might want to calculate quantities in. Okay, so we've got this 2 megaparsec sphere. Physical objects select data are called data objects. And the way we initialize a data object, for example, a sphere is very simple. We have this ds, which was our dataset object that we loaded earlier. We call a method called .sphere, and we give it two quantities. We tell it what the center is. So in that case, you can feed it like a 3-element numpy array or a list in Python telling you the coordinates in x, y, z. Or in this case, I'm just going to give it the string max, which tells it to look for the max density, and then say that's going to be the center of the sphere. And the next element is a radius, which again can be just a plain number corresponding to the radius in code units. But YT is unit aware, so I'm saying I want a radius of 2.0 megaparsecs. So that is completely sufficient, obviously, to define a sphere, a center, and a radius. And so I say ds.sphere equals sp, and that gives me my sphere object. If you look at the output here, the standard out info, noticing it actually bothered to look for the max value of the gas density, found it, told you where it was. That's where I'm sticking the sphere. And the nice thing is that now you don't have to think about, what resolution is the data, what sizes are the cells, where are they, that sort of thing. Or even if they are cells, maybe they're particles, maybe it's an SPH data set. YT is dealing with the multi-resolution data for you under the hood. So we can imagine all these cells that were inside the sphere. We can imagine them unrolled into a single 1D array. And if you query the sphere object and say, give me the density, so this is standard Python syntax, like basically dictionary-like syntax. So print sp, density. What it will do is that it will return a data array. If you're familiar with Python, this is a numpy array. This is basically like a 1D numerical array like you would have in C or Fortran or anything like that. And it will give you the density in that sphere as a 1D array with units attached. And I'm going to be showing units throughout the talk, but we'll go into more depth here in a little bit. Now, density is obviously not the only field you can look for. You can actually query the sphere for the temperature field. So it's giving us the temperature field here in Kelvin, which is good because that's the units. I said that you don't have to worry about the spatial information unless you really want to know what they are. And so you can also query fields like the positions of the cells. So in this case, we're looking for the position along the x-axis. It's returning an array here. Notice the units are a little weird. Again, we'll be getting more depth in the units later. But remember, this data set has units, code length, of 0 to 1. So it's giving us the positions in code length. But I can always convert to something else, right? Because maybe, in physics, I don't care about code length, right? So what I care about is something like kiloparsec. So I can do, say, x in the sphere, convert it to kiloparsec, and that's how I would do it. Again, we'll be going into more depth later in the talk about that. And we can also query things like the cell sizes. So we can ask for the cell size. In this case, dx, again, the dx along the x direction. You can also do it for dy and dz. And here I'm just calling a numpy method to basically sort through the dx's and only giving back like the unique ones. So we're showing basically that there's 5 levels of refinement in this simulation, and these are the dx's that correspond to each of those levels. So in order to be inside the sphere, the center of your cell has to be within the radius. Yeah, that's right. Eventually, I think we're looking for more creative ways of handling it, but at the moment, that's how it works. So I've been showing you a sphere example, and I apologize, these pages are not rendering exactly on the notebook like I wish them to, but there's a link on our page showing you all of the objects that you have access to. So we have 0D objects, which is, you can have an object for a point. You can say, what's the density here? 1D objects like rays that are either aligned with an axis or off an axis. 2D objects like slices, whether along an axis or again, like a cutting plane, which is not aligned with an axis. Boxes, disks, cylinders, that sort of thing. Here's some examples of how you would initialize some of those. There's a lot of detailed information about how this works in our documentation. This is, again, is just trying to be an overview of just the different things you can do from like a bird's eye view. So you can initialize all these different objects, like a rectangular solid, like ds.box. You can query it for the fields in the same way that you can do for the sphere. Same thing with disk, ray, etc. So I keep mentioning fields. So I should probably mention a little bit about how YT thinks about fields. First of all, as you probably already can tell, what I mean by field is basically just what's the value of data for a particular physical variable in, at a particular point, as a function of space. So we can have density, temperature, we can have vector fields like velocity, magnetic field. So every data set has an object called a field list, and I just say print ds.fieldList. It will tell me all the fields that are associated with the data set. What I mean by that is that these are the fields that are stored on disk. So because this is an ENSO data set of cosmology, it's got dark matter density, electron density, gas energy, a bunch of species fields, temperature, velocity fields. Sorry, that won't let me scroll. Some of these other fields are associated with the particles. We make distinctions between particle fields and fields on the grid, but the particle fields are still there. Now, the other thing that we have in YT is we have the concept of a derived field. So say you have, say you only had like density and temperature in your data set, but you knew that, the physics of the simulation was such that, the pressure was just, derivable from those by the ideal gas law. We have basically rules for derived fields which could let you compute the pressure and query the pressure field from the sphere or the box or whatever it was, without having to multiply them yourself, basically. So here I'm just showing an example of all the things that are in the derived field list. I cut it off at 20. There's a lot of, this is not probably a very interesting sample, but all these fields happen to be related to all the different species in the simulation. So, as I mentioned, there are particle fields. So if I just look at the particle fields in the data set, this is a combination in this data set of star particles and dark matter particles. So they have positions, velocities, masses, indices. The star particles have a creation time field and a dynamical time field. And this is just showing that you can query the particle fields in the same way that you can query the grid fields. So you can ask for, so I can create an object like this. It's similar to a sphere, except this is like all the data on the on the highest levels of refinement in the data set. And I can query that object just like I did the sphere, and I can ask for the particle position, which is actually a numpy array of like 3 times the number of particles because it's, it's a vector field. And I can also ask for the mass. And there's also a concept of deposit fields. So if you have a data set, which is, basically a grid-based data set like this one, but you also have particle fields, there are also deposit fields that automatically get created that allow you to look at the density or the other whatever quantities you want actually from the particles deposited onto the mesh. So if your data set, for example, doesn't automatically include, say, like, a density field based on the particles, you can actually create one. So it creates at the resolution locally, because because in general these are adaptive mesh simulations and the resolution is changing. It will deposit the particles into the cells locally. Now, what these different names refer to is that it uses a few different methods. So CIC refers to a cloud and cell deposition, which is a fairly common one, but you can also have just like straight, whatever particles are, within this cell boundary, just dump all the mass from them in there or something like that. This shows an example of, you don't have to rely on the derived fields that we define. You can create your own derived fields. So if I have a function called myEntropy, say you didn't have an entropy field, either in the simulation or in YT, although we do give you an entropy field, you could define one on your own. So I'm importing some physical constants, which I'll get to later more in the unit section, and I'm defining the entropy field, at least in a way that galaxy cluster people would think about it. So that's this KT over the number density to the 2/3 power. And I call a method ds.addField. I tell it what the field name is, entropy. I tell it what the function is I use to derive it. And I tell it what the units are. And then once I've created a derived field, or once I've used a derived field that YT provides, again, remember, a derived field is one that's not in your disk data set, I can ask for it in exactly the same way that I asked for the data for the field that was on disk. And this is actually like, this is one of the main goals of the field system, is to employ what we call a field democracy, or in other words, that every field in YT is a first-class citizen. There's no, you can manipulate fields and query them and ask for them and do things with them, whether they're fields on disk, whether they're derived fields that you've created yourself or whatever, in the exact same way. There's no difference, basically. And that would make sense, right? Because from a physical perspective, your plasma has a density and a temperature and a pressure, and you don't particularly care whether or not the pressure field is in the output file or not, right? You want to know what it is, just like you don't want to know the other ones. The way we achieve this is that even if your field is on disk, it's basically treated as a derived field. We just map the field that's on disk to a derived field, so that everything is essentially a derived field, even though when we say that, we usually just mean the fields that get derived from combinations of other ones. So for example, Enzo has a field called Enzo comma density, where the density here is capitalized for some reason I've never understood. But this is just alias to the standard gas density field. The other thing that's really important about this is that if you have a data set, say if you have a script that works really well in a data set, say you have an Enzo data set, but the person down the hall from you works on flash data, but they could probably use the same script you're using with minimal modification. They don't have to change the field specifications to make it flash aware. YT is just going to use the density field because it knows how to map from an Enzo density field to its density field, and a flash density field to its density field. Okay, so I've been showing a lot of units and a lot of manipulations of units without much explanation, so let's get into the guts of YT's unit system. So we've already seen how data objects return fields as unit-aware numpy arrays. This is a symbolic units implementation using SymPy. If you're not familiar with that, it's kind of like, SymPy is a package in Python for symbolic mathematics, kind of like Mathematica is. And what we use this to do is to basically do, basically carry through units in terms of unit conversions, unit arithmetic, things like that. So here's just a quick example. I have the density, I have the temperature. Earlier I imported the Boltzmann constant and the proton mass, and if I want to have a rough calculation of the pressure, I can just multiply the density and the temperature times the appropriate combination of constants and give me a pressure array that I could say, I want to put that into pascals. Not sure why, but you can do that. And it will give you the answer in pascals. Or I could say, I want it in units of dyne per centimeter squared, and it will give it to you right here. So what's going on here? Well, YT is very flexible handling for units and unit conversions. So suppose I take the density from the sphere earlier and just assign it to this array, rho, and then I can query and say, well, I can use this in units method to convert to different units. So I can say in units of grams per cubic centimeter, which is kind of superfluous because it comes in that by default. So that's this right here. I can say in units of solar masses per kiloparsec cubed. Give it to me right here. If I want to give it to me in code units, if I'm curious about that, the default code units of the data set, which I mentioned earlier, you can do that as well. For unit systems that you might use fairly frequently, there are shorthand conversions. So for example, I can do rho in underscore MKS to give it to me in kilograms per meter squared. And I can do rho in underscore CGS to give it to me in CGS units. And that will work for any, we call them YT arrays. So that's a numpy array with units. Those will work for whatever one. It will just figure out what dimensions it needs to do it in and do the conversion. Besides CGS and MKS, other unit systems are available. This is a new feature in YT 3.3, which I should have pointed this out at the beginning of the talk. This is what I'm running this presentation out of. It's in our dev branch, although it will be released within the next few days. The installation instructions that I gave that should be on the website shows you how to install this dev version right now. We just went through a bunch of bug fixes, so it's basically a release candidate. It should be officially released later this week. But we have some other examples of some unit systems. We have a unit system registry. This is kind of Python-y here, but I can list the elements of the unit system registry. You can see we have CGS units, imperial units, MKS, geometrized, Planck, galactic, solar units. And if I ask that unit system registry for one of those, it will tell me what the base units are. So the base units for those, so for MKS, we have kilograms, seconds, meters, kelvins, amperes, and then some other units that we also define that might be useful. So here you have the usual suspects, joules, pascals, Tesla. Let's look at some of the others. If you really want to calculate, a galaxy's temperature in Rankine, you can do that using the imperial unit system. Or if you wanted to calculate the density in pounds per foot cubed, you could do that. For you relativists out there, we have a geometrized unit system. This looks a little funny, LGeom, MGeom, TGeom. These are placeholders because we have to keep track of the dimensions. We have to keep track of what the dimensions are, even though all of these are essentially equal to one solar mass. But this is something we also added recently. And so we can convert rho into other systems like I did here. Here's me converting a galaxy cluster's density into pounds per cubic foot. But don't do something ridiculous. What would something ridiculous look like? Maybe this. Say, hey, I want the temperature from a sphere. Convert that to kiloparsecs. So if I try to convert temperature to kiloparsecs, it will say unit dimensionalities do not match. Try to convert between K, dimensions of temperature, and kiloparsec, dimensions of length. So it's smart enough to realize when you accidentally had like a typo or something. Now, you don't have to just rely on the unitful arrays from the data set. You can also create your own arrays. So if I just create a numpy array of random numbers, I can give it to this YT array function and give it units, and it will give me an array of units of kiloparsecs. We also have YT quantities, which are just scalar numbers, so just floats. We can also give those units as well. So in this case, I'm creating a YT quantity with units of ergs per second per centimeter squared per steradian. If you're an X-ray astronomer, you might care about numbers like that. There are other ways of getting at units. So we have a YT.units module that we can import, and it's got unit quantities for most of our base units. So if I import YT.units as U and then print U.kiloparsec, it gives me a YT quantity with units of 1 kiloparsec. And then I can take a numpy array of anything and multiply it, say, by example, by U.kilogram times U.centimeter divided by U.second, and it will give me something, just like a little momentum array here, basically. Physical constants are also in the unit system. You've seen some of these already. From YT units, import, for example, G, K bolts, H bar. They have the values in the units you would expect, hopefully. You can see these are all by default in CGS, but you can ask for them in a different set of units. So for example, in this galactic unit system where the mass, length, and time are solar masses, kiloparsecs, and mega years, you can get the constants in those unit systems as well. There are a few other things in here. You can see Kelvin remains the same because I'm not sure what else we put in there. As we've already seen too, every data set is a set of code units. So here I'm showing what the code units are in length, mass, time, velocity, and magnetic field for this particular data set. So you can see this is actually a cosmological data set, so the default length unit is co-moving megaparsecs, sorry. And if you want to create your own array in code units, you can do that. You don't use the YT array function. You use something that hangs off the data set. You use ds.r, and you can create a data set in code units. The reason why you can't use that without a data set is very straightforward. Like, code units only make sense within the context of a data set. So you can do the same thing with quantities using ds.quan. So here I've created a quantity of code mass divided by code time squared divided by code length, which happens to be units of pressure, and I can convert that into kiloelectron volts per centimeter cubed. And basic arithmetic and most numpy functions work on unitful arrays out of the box. So if I want to take rho, which is in grams per cubic centimeter, add it to something that's in solar masses per kiloparsec, it will happily do it. It will convert the units of the latter to the units of the former because they're the same dimensions. It will add them together and give you the answer. There's a numpy function called squirt. It does what exactly we'd expect it to. It takes the square root. So I'll take the square root of the density. It will take the square root of the array, and it will give me the square root of the units. Squirt G divided by centimeters to the 3/2 power. And I can also multiply, so I'm just going to multiply rho times the velocity x from the same sphere, give me a momentum density. But again, don't do something silly. What if we tried to add rho plus the velocity? Well, those aren't in the same dimensions either, right? So, but it won't chide you too much. It will say the addition operator for YT arrays with units of grams per cubic centimeter and centimeter per second is not well defined. It won't say, that's crazy, why are you doing that? And say, look, I don't think you can do that. So we've looked at the data objects, we've looked at the querying the data arrays from the data objects, but what if we want to derive quantities from these data objects? So we have derived quantities which turn fields into single values. So what do I mean by that? Well, suppose you want to know the total mass in the sphere. You can query a field called cell mass, which tells you what the mass is in each cell of the sphere. Gives you that array that we discussed already. But I can call it derived quantities, so in this case it's sp.quantities.total quantities cell mass. And you add up the mass of the cell and return it as a single scalar quantity with units. Here's another quantity, sp.quantities.angular momentum vector. It will take the actually this is the specific angular momentum, but it will take the angular momentum of the system in the sphere, and it will add everything up and return the angular momentum vector. So this is an array, obviously, of 3, because it's a vector. Again, this did not show up at the place where I thought it would. We have other available derived quantities: bulk velocity, center of mass, extrema, maximum location, minimum location, spin parameter. These are all things you can ask of the data objects. This is also a relatively new feature. This is kind of just a different way to achieve some of the same things, but YT has another way to create rectangular shaped regions using numpy slicing syntax. So for example, if I do ds.r and I give it a slice like this, which if you know about numpy arrays, this should look familiar to you. This is essentially asking for the entire array because the colons for each dimension run from beginning of the array to the end if you don't give it any numbers. So that gives me a region. And then I can do operations on it. So dd.mean density gives me the mean density. dd.mean temperature. I can also give it a weight argument, and it will give me the mass weighted temperature. dd.argmax in numpy, argmax on an array gives you the indices of the maximum value of the array, but in YT it gives you actually the coordinates of the maximum value, which would be more useful in this case. But if you wanted to know what the values of other things were at that point, you could just do axis, density, and radius, and it would tell you what the density and the radius were of the cell that had the maximum temperature in this case. Now, obviously, if I'm showing you like a numpy slice, you can obviously do selections. So here I'm slicing the data set on coordinates. These are obviously in code units because remember in this particular case it ran from 0 to 1. If you have different code units, it might run from like something else to something else, but here's just a subset of the box, and I can do the exact same things. If I'm a bit more creative, I can use YT arrays to do something very similar. So I'm setting C equal to the domain, the center of the domain using this ds.domainCenter, which is a YT array for just the coordinates of the domain center. I'm saying I want a box of width 5 megaparsec, and then I'm defining a left edge and a right edge of the box based on that center plus or minus half the width. And if I slice using those arrays, so left edge, right edge 0, left edge, right edge 1, left edge, right edge 2, so basically x, y, z. I get a region, sorry, I'm skipping ahead, that corresponds exactly to that subset. Are there any questions at this point? I know I'm going through a lot of material. Go ahead.
I'm seeing a lot of numbers with 10 to the minus 30.
Yeah.
How do you handle numerical precision? And if you do a query, for example, on a data set that has very small values, to add it up, do you lose information?
So first of all the numbers so we're operating in double precision on all these operations. For some mathematical operations, what you're talking about can get really nasty. So for example, computing a variance can be like loss of numerical precision can be a big issue. So for some operations, we're actually taking care to make sure that we use algorithms to compute those that minimize the loss of numerical precision. The other thing I should mention is that all these objects I'm showing are chunked. So in other words, like the operations occur on subsets of cells. That's mainly to aid in like memory, but also it might mitigate some of those issues as well. So, but that's a good question. I think I'll have to think a bit more in depth about though, in terms of how, in other ways that we might be handling it. Obviously, these numbers are really small because it's for a particular astrophysical system and it's in CGS units, and so.
I have a question.
Yeah.
What about the geometry supported by the core of YT?
Sorry.
Different geometries.
Different geometries?
Yes.
Okay, so we have absolutely excellent support for Cartesian geometry. We're working right now, doing a lot of work right now on other geometries. So we have some basic support for spherical and cylindrical geometries. Not everything works yet, so I think a lot of what I've showed you right now, most of that should work in terms of like, just querying different, objects and asking, what's the total of this or that or whatever. Most of that's work. A lot of what doesn't work quite yet, not all of the visualization I'm about to show works.
And how do you deal with staggered quantities when you have derived quantities? For example, the momentum. When you multiply the density by the x velocity with the staggered quantity, you have the momentum defined in one edge. If you compute the momentum in the perpendicular direction, you have the center of this quantity is different from x
So are you asking for like how do you compute like a magnitude or something like that? Or so we have, so as far as magnitudes go, we have helper functions that compute magnitude fields from vector fields. Some of them are already defined. So the velocity magnitude is for example, is a field that's already predefined. Same thing with magnetic field. I'm not sure if that gets.
You showed the example with the momentum, density plus x velocity.
So density plus x velocity gave me an error, right? Because that makes no sense. I can't add a density to a velocity. I can multiply the two, and that does work, right? And that gives me a momentum. That gives me a momentum flux. But if I no, sorry, that gives me a mass flux. Pardon me. So.
I want the total momentum.
So you want the total momentum. So what you can do there is that you can do, you can add Vx plus Vy plus, well, you would have to use a magnitude field then, right? Because you need something, you need like the sum of squares, square root. So we have a helper function that computes like the magnitude of a field, of a vector field. Does that make sense? Or anything else at the moment? Yeah. Yes, that's only in version 3.3. So everything, you should assume that a lot of this works in 3.2, but you should assume 3.3. And did the installation instructions for 3.3 get up? Okay. Yeah.
So how far does the numpy functionality extend with the array? Like, can I do conditional statements and then use arguments and indexing the same way I would with a numpy array?
Yes, in most cases. You might hit, so if I think about the source file that contains all this, there's a big long list of all the numpy functions that we support. So I think you would be hard pressed, you would have to be in some obscure operation basically to find one that didn't pass the units right through. And if you were to work with one, you would find one that didn't work the way you would expect it to. I would definitely, as I'll give the ways to do this later, I would definitely submit a bug report and say, hey, this is supposed to work, because we love fixing things like that. So, yeah. Right. So for example, in many MHD simulations, you'll have face-centered variables like the magnetic field, for example. That's something we don't support yet. We're planning on it. So because that's a big use case, for a lot of people, especially in this room. So, and for me as well. So, okay, I'm going to move on, but I think we'll have some more time for questions at the end. So, okay, so now I'm going to go into some of the visualization and analysis. We'll get into some pretty pictures. So the simplest thing you can do with a data set is take a slice through it. So we have a way to do this called a slice plot. So a slice plot takes a data set, it takes an axis, it takes a field, a single field, or a list of fields, and it takes other arguments that I'm not showing here except for one of them. For example, I'm going to take the center of the slice to be the maximum density, but you could also put, like I said, a coordinate in here. There's also a width argument. There's a whole bunch of different arguments that this function takes to create different slices. But if I just took this slice and called .show on it, because I'm in a Jupyter/IPython notebook, I get this. Now, unfortunately, this data set is not the greatest, because you can see it's terribly low res. But that was so, it didn't take you forever to download it from the website. So I have a second data set that looks a lot better. But this is, like I said, this is a cosmological simulation, so this is exactly the sort of thing that we would expect. We've got filaments, we've got clusters forming at the intersections of the filaments. You can see that by default, the slice places the origins of the coordinates at the center of the slice. You don't have to do that, though. For example, you can say slice.setOrigin native, and then it will place the coordinates in the native dimensions of the data set. So, for example, this ran from 0 to 1. Right, so in this case, we're catching, this is a periodic data set, it's a cosmology data set, right? So in this case, we happen to be catching a cluster near a boundary, so you can see that we're actually wrapping around to the other side of the box here. Okay, so what if I wanted to take another data set? This is the other data set that I haven't shown at all yet in this talk, but this happens to be my data set. This is a Athena data set that's been converted to a slightly different format just to make life easier for this talk. Here I'm taking a slice plot of the magnetic field strength perpendicular. So the slice is taken perpendicular to the z-axis, and I'm telling it that the center is C, which corresponds to the domain center, and the width of the slice is 500 kiloparsecs. And that's what that looks like. So this is a slice through the magnetic field strength. You can see we've got the correct units here in Gauss. We've got 1 microgauss right here. Like Matt said this morning, everything is in microgauss. Going back to the cosmology data set for a moment, I'm going to be flipping back and forth between them. You can easily change the color map. We just heard a really excellent discussion of color maps, why you should preferably use some and not others. Some are better perceptually than others. Here's one. I'm not sure how well it's doing perceptually, but this is a color map called Magma. You can use the default matplotlib color maps. That's the Python library we use for plotting, or you can use some of the ones we've added. When we developed YT, somebody added in a bunch of IDL color maps. I'm not sure if you'd want to use those or not, but they're there. If I'm taking a slice and I'm curious to see what the grid structure is in an AMR data set, I can call annotate grids. This is an example of a plot callback where I throw something on top of the plot. So this shows you where the boundaries of the AMR grids are. Let's go back to that galaxy cluster data set. Annotate magnetic field gives me the magnetic field vectors. Now, as you can see, this is kind of messy. The vector length depends on the strength of the magnetic field in the plane, which is good, right? But say we wanted unit vectors, or we wanted to change the spacing between the vectors, or we wanted to change like the length of the vector on the plot that corresponds to the magnitude of the vector. These are all options that you can stick here in this call that I'm not showing here, but it's in the documentation. We can also annotate streamlines. So here I'm annotating the streamlines of the x and y velocity, since we're taking a slice perpendicular to the z-axis. So you're seeing that here. You can also have more fine-grained control over this. You can control the colors. You can control the the number of streamlines, the density of them, rather, that sort of thing. But the next slide is something that Soqing added to YT. I think this is really cool. You should ask him about it. These vector and streamline representations of vector fields don't necessarily always do things such justice because by definition they're coarse, right? You don't always get like a really fine-grained representation of what's going on with the vector field. So he added a line integral convolution. So this is a line integral convolution of the magnetic field, and you can see the more detailed structure of the magnetic field, at least in this plane right here. So you have a slice object, and when you're satisfied with it, all you have to do is call slice.save, and it will save it. You just say myamazingplot.eps or myamazingplot.png, or I think JPEG works too. In the next few examples, I'm just going to show that you can do the exact same thing, as you're probably not surprised to hear based on what I said earlier, using derived fields. So here I'm deriving fields for the sound speed and the Mach number, which I didn't have to do because they're already in YT, but they're nice, simple examples. So I'm defining the speed of sound and the Mach number, telling them that they have units of centimeters per second and nothing in case of the Mach number. And I can plot that in exactly the same way. Here I've zoomed in a little bit. The width of this slice of that same data set is now 200 kiloparsecs. And then if I decide that I want to change the units of the plot, I can do that. So I'm changing the units of the sound speed field to kilometers per second. If the field is logged, I can unlog it, or I can make it linear, or I can make it log just by doing setLog true or false. I can set the limits of the plot in terms of the color map. So here I want to make the color map run from 600 kilometers a second up to 1,000. I'm doing something similar here with the Mach number field. Okay, I'm going to move on from slice plots to projection plots. Hopefully, most of us in here talk to observers. I have to on a daily basis. So, and obviously the objects we're looking at are projected along the sky, so it might be interesting creating projections. So here's a projection of the galaxy cluster data set of just the gas density projected along the z-axis. And this is a really bad example of how the choice of color map and the brightness of the screen don't match up very well, but this is what that looks like. If you've got a keen eye, we're actually zoomed very far out in this case. All of that spiral structure you saw is like right here in the center. But there's actually a shock front right here because this galaxy cluster has undergone a merger, so there's a shock front if you can see the edge up here or not. On either slice or projection plots, I can call a zoom method. So I'm zooming here by a factor of 20 to bring us back close into the spiral. I can zoom in by another factor of 3. We're getting down into the core. Now you can see the resolution here. The resolution in this simulation is a kiloparsec, I think. There's also I'm not showing it here, but there's also a set width method, so you can set a new width after the fact. Even if you've already given it a width, you can say, hey, now I want a width of this. Here, I'm just going to show you projections along the different axes. So that was z, x, y, just looking at the spiral from different projections. There are off-axis projections and off-axis slices. Again, I'm not showing them here for lack of time, but that's definitely something you can also do. Say I want to take a projection, but I don't want to look at all the data. Say I just want to only project like a portion of the data in the domain. So, for example, I can create a sphere object, say around the maximum density in the cosmology data set. The sphere has a radius of 5 megaparsecs. I create a projection plot, but then I pass this extra argument called a data source. I say data source equals SP. And if you look at that plot, it's mostly nothing except for that right here. You can define regions based on field cuts. So for example, there's a way to define a region. Say, give me a region that has all the gas with a temperature higher than say 5, kiloelectron volts. And so that might be a more sensible thing to project or to take a slice through or something. So some projections make more sense if they're weighted projections. So this is a projection of the temperature, KT, that's weighted by the gas density. I should point out that the way the plots handle the units for these projections is that if you're just doing a straight, integral projection, it will take, say a density, in grams per centimeters cubed, and it will convert it to grams per centimeter squared. But since this is a weighted projection, the units should stay the same, and they do. We also have a different kind of projection that's not like an integration of along the line of sight, but also a maximum intensity projection, which instead of doing a line integral along, a particular line, what it does is that it finds the maximum value of the the field along that line, and then that's what it returns as the projection. This is not as, at least it doesn't seem as physical to me, but it might be useful in some kinds of visualizations. So that's what's going on with this for the density. It's a little grainy here, but in that case, the units should stay the same. They should not, you're not multiplying by a path length in that case. So that's what's happening here. And if we go back to that numpy slicing syntax I showed you earlier, we can create slices and projections from that too. So for example, before I was slicing on, all 3 axes. What if I just took a single number slice along one axis, in this case the z-axis? Gave me a slice. I asked slice.plot density, and it gave me a density plot. Let me scroll that down. We can do the same thing with projections. So here I'm creating like a subset of a box, and I want to integrate the density along the x-axis. It gives me something like that. And I can also do weighted projections. So this is a weighted projection of the gas temperature along the z-axis, x-axis, sorry. And we also have different options for projecting particles. So we have a particle projection plot. Here we're projecting the particle mass. Now what this essentially does is that you can tell this is essentially a glorified scatter plot. So what's happening here is that we're just throwing the points that correspond to the particles onto the plot, and then we're coloring them based on, you know, the mass of the point. So here we're looking at particle mass. You can see the, you know, the dark matter component of the clusters here forming at the filaments. But I mentioned the deposited fields earlier. And this is an example of a projection of a deposited field. It's a little crabby because this is a low resolution data set, but you can see this is kind of exactly what you'd expect. Nice big void here. In fact, there's apparently nothing going on in this cell right here. So. And we also have other kinds of plots. This is a phase plot. So a phase plot is, think of it as a 2D histogram. Okay, so this might be really useful. So suppose you wanted to know what the mass of gas was at a density of, say, 10 to the minus 29 and a temperature of 10 to the 6. So that would be right about here. So I'd look at the color here and I'd read the color right off the color bar over here. So in this case, so this is showing me all of the data in the entire simulation, essentially binning it up into a 2D histogram. So I set fractional equals true, which means it calculates a normalized probability density function is essentially what you're looking at here. But if I didn't set that, it would tell me what it was and say like solar masses or whatever mass units you wanted. Okay, so the last, how am I doing on time? Okay. So in the last bits of the talk then I want to talk about just some extra analysis tasks. So we'll talk about profiles, fixed resolution buffers, covering grids, and unfortunately there are a lot more things that I don't have time to talk about in detail. But I think these are, at least in my experience, have been some of the most important ones. We already saw a profile just a couple slides ago. Profiles are essentially just a 1D, 2D, or 3D histogram of a field versus a set of other fields. So that bend phase plot I showed you is a 2D profile, basically. You can use profiles to calculate the average value or total of a field versus another field. So for example, say I make a sphere from that galaxy cluster data set with the magnetic fields. I place the sphere at the center, 300 kiloparsec sphere. I use this function called create profile. I tell it I want a profile bend on the radius of the density. So what we'll do is it'll create a set of radial bends in one dimension. It will compute the average density within each radial bend. There's some extra arguments here that you can put in. This is just happening to say don't compute log-spaced radial bends, compute like linear-spaced radial bends. You can also set like, if you want the field you're averaging over to be weighted by something, you can also, there's also like a weight argument to do that with. So it creates a profile object. And this is not a YT plot, this is a matplotlib plot, but what I'm doing here is that I'm asking the profile what the radial coordinate is and what the density is. And I'm just feeding those into matplotlib's log-log plot, and I get a log-log plot of the density versus radius. Okay, so the next thing I want to mention very briefly is the fixed resolution buffers. So I've already showed you slices and projections. These are essentially 2D maps. And I showed you how you can use YT's methods to make a plot, but suppose you wanted a two-dimensional array that was uniform, say nx by ny, uniform resolution, and you wanted to manipulate it somehow. Say you wanted to put it through your own imaging package, or you wanted to multiply it with another similarly shaped image. So we can create these, we can use these slice objects and the projection objects to create what we call fixed resolution buffers to do exactly that. So, and that's exactly what's happening under the hood in the slice plots and the projection plots is creating like a fixed resolution image array. you can do that yourself. So for example, I'm calling ds.slice. It's a z-slice along this particular coordinate and code units. Then I call another method slice to FRB, that stands for fixed resolution buffer. I say I want this buffer to have a width of 40 megaparsec, and I want it to be 800 cells on the side, which is a little arbitrary, but that's just the number I picked. And as with all the other objects in YT, you have to query it for a field. Here I'm using just, again, a pure matplotlib function called imshow that just shows you like color map images. But I'm doing the fixed resolution buffer of the velocity magnitude. And that's what this looks like right here. It's not quite as nice as the YT plots. But again, if you want to manipulate 2D images directly, you would use a fixed resolution buffer. A similar concept in 3D is a covering grid. So we have covering grids where you can define like a fixed resolution 3D region of space and create a covering grid in XYZ, basically, that you can either just sample over a particular region and inject the values of the cells, no matter what resolution they're at, into the resolution of your grid, or there's also a smoothed covering grid that you can interpolate values between cells of into the cells of your covering grid. And this is if you want to avoid thinking about AMR. For example, if you need to have a uniform resolution in 3D for some reason. So one example would be if you wanted to take the fast Fourier transform of a region, for example, you create a covering grid and you could do that. So here I'm showing a slice plot of the velocity z of the galaxy cluster simulation, which you've already seen, nothing new here. But here I'm creating a covering grid, and there's a lot of detail in here, so I apologize, but I basically tell it an effective refinement level I want this at. I tell it the left edge of the grid I want. I tell it the dimensions of the grid that I want. And then what it does is that it determines like what cells belong to that grid, and then if I ask for a field, it will put the field in there, and then I can use that in the same way I would use a standard numpy array to plot it in matplotlib or something else, basically. And as I said, there's also a smooth covering grid, which does like a better interpolation. Like covering grid is just kind of doing like injecting values of cells into the cells of the covering grid, which often you may not want. So wrapping up the talk here, I just want to mention a few other things without going into detail. We also have analysis modules in YT that carry out specific kinds of analysis tasks. So this is our web page again. We have halo finders for cosmological simulations. We have synthetic observation modules. So there's synthetic observation modules for creating and fitting absorption spectra, X-ray emission fields. If you're a cluster person, there's a mock Sonyaev-Zeldovich effect module. There's a mock X-ray observations module that I wrote. There's a module to create what's called a PPV, or a position velocity fits cube. So you create a fits fits file that's got, say, X and Y or RA and DEC on the sky, and then the third dimension is, say, velocity or wavelength space. YT just basically creates a bunch of projections for all these velocity or wavelength bins, and then creates a fixed cube out of it. And there's some other things in there as well. One of our most popular features that unfortunately I don't know as much about, I think So-Ching knows more about it than I do, so I'm sorry I keep giving you stuff to do, but we have a really nice volume renderer, and this is showing you the documents for our new volume rendering stuff in YT 3.3, which we've recently changed. I'll show you, once I quit out of this notebook, I'll show you a nice movie of a volume rendering that was made. Okay, so maybe some questions. So I'm at Princeton, so I feel like I need to answer this question. What about Athena++? So if you were working with Jim and the others on Athena++ data, you might have noticed, or maybe you didn't, but in any case, Athena++ was not listed in the supported codes. That's because the support for it is existing solely in my particular YT repository. So if you'd like to get the code for that, you can talk to me about it, but I'm hoping it will be merged into the main development branch probably after the Athena++ release. So what I've shown you is, basically ways to avoid thinking about the resolution, the particles, the AMR, all that stuff. You're like, but what if I want to look at the data from the perspective of the way it's laid out in the mesh? What if I want to see the values of the density in a block or a grid or something like that? You can definitely do that. Each data set has an index object that holds the mesh hierarchy. What do I mean by that? Well, there's an object ds.index, which knows about the grid metadata, know which grid is neighboring which one, what children it has, that sort of thing. And it has an array called grids, which is just an array of grid objects. In this case, this is that ENSO data set. So this is not very illuminating. It's just showing you all the grids in the ENSO data set. But if I, basically indexed individual grids, I could determine things like the left edge of the grid, the right edge of the grid, the dimensions of the grid. And I could also query each grid for the density. It would return me a 3D numpy array with units, of course. Or you might have noticed that your favorite code doesn't appear to be supported. Or maybe you have just a derived data set of some kind, and you still want to use some of the functionality I showed. For a start, we have ways of loading in array data that's sitting in memory, either derived from their data set or from a code we don't support yet. We have methods for loading uniformly gridded data, load AMR grids, loading particle data, hexahedral mesh, which is a semi-structured mesh data. If you have the talk in your web browser, these are actually links to the different parts of the docs that show this. So when people who want to get their data into YT, but their code isn't quite supported yet, what we normally do is we point them in this direction. And once we can get it working in here, then we think about ways to actually support their code efficiently. The most important reason why the difference between those two things is that for all these methods, even though you load the data in, and you treat it in the exact same way, in this case you have to load all the data into memory first. Whereas if you have a supported code like Flash or Athena, what it does is that YT determines which cells it needs before it even bothers to go to the file, and only only downloads the cells of the particles for the file that you asked for, say in the sphere or the slice or whatever. And so it's very memory efficient in that way, but if you have to load everything into memory, it kind of kills that. But it's a good place to start anyway. I already showed some of them, but the new features in version 3.3 are first-class support for unstructured meshes, an improved volume rendering interface, interactive OpenGL volume rendering, where you can take the mouse and kind of scroll it around and watch the volume rendering. Easy conversions between different unit systems, which I already showed, NumPy-like operations. Coming soon, this already came up, improved support for non-Cartesian geometries. So you already have some support, but it's our intention to really press forward on this very quickly so that we have just as much support for those as for the Cartesian. Improved scaling for data sets with particles and streamlining the process to get data into YT. We want to make it easier for people to get data in, even if their code's not supported. We don't want to have to resort to those load functions I was just mentioning that require you to load all the data into memory. So we're working on creating a process which you have a file, you create a text file called like a YAML file, which basically gives you a basic bare bones description of the file, and then YT will process that and learn how to read in the data from that. So that's hopefully coming down the pike at some point. One of the most important things about YT is community. So since the inauguration in 2007 with the 3 scripts that Matt Turk had on his laptop, which was the beginning of YT, over 20,000 change sets have been submitted by over 100 unique contributors. We have 350 subscribers to our users mailing list and 120 subscribers to our developer mailing list. It's our intention as a community to blur the line between these two communities. We really want to lower the bar for contributions. And if you want to learn how to do that, you can definitely ask me about it. Basically, the way that usually people get started with contributing to YT is that they start using it and they run into something that they wish it could do, but it doesn't. And then they email the mailing list and they say, well, it doesn't do this. And then we're usually like, oh, that sounds really cool. Maybe it should do that. And so then we work through the process of, developing the code and submitting a pull request and things like that. And we'll be talking more about code development later in the workshop. You'll get the meanings of some of those terms, but we definitely have workshops, we have code development meetings. I'm in a couple of these pictures here. Funding for aspects of YT development comes from NSF, NASA, and the Gordon and Betty Moore Foundation. So getting involved and asking for help, we have documentation on the website. There's the 2 mailing lists I mentioned. There's the users mailing list for people who just want to know, hey, how do I do something, or this broke. Developer mailing list for people who want to get involved in development. There's a developer guide for that as well. Peter's encouraged everybody to use Slack for this workshop. We also have our own Slack channel where anybody can get on and you can talk about how to use stuff, ask questions, get involved in code development. Also, we have an IRC channel, #YT on Freenode with your favorite IRC client. And I think that's my last slide. So what I will do now is that I will close, as promised, with a volume rendering. So this is from Sam Skillman. This is actually a bit old, but still pretty neat. So this volume rendering was created entirely in YT, except for the star backdrop. That's just for effect. So here we have a galaxy cluster forming at the intersection of filaments, and these are density isocontours. And you're seeing, not only can you step through the simulation itself over time, but you can also pan and zoom and rotate and things like that in the volume rendering. So.
So it might be interesting to mention that this is the one that made the cover of Nature, right?
No. So the volume rendering that made the cover of Nature, it's good you bring that up, because that was not a volume rendering of a simulation. That was a volume rendering of NGC 253. Is the volume rendering of a PPV cube. So it was actually not a simulation, it was an observation. So it was sort of the first example of pushing the boundaries beyond thinking about simulations only, but thinking in terms of astrophysical volume oriented data in general. So. Okay, so with that, if there's any time left, I'll take a few more questions. Thanks.